In the previous video, we talked about looking for patterns within sequences of remainders. In this video, I want to talk about a different sort of pattern that appears within remainder problems, and that is a pattern within literally the way they are presented on the GMAT, meaning the way they are actually worded on the test. And so I have a bunch of questions here, a bunch of remainder problems. I pulled these all from MBA.com, so credit to them. And the point here is not to actually do these problems now. I just want to read them so that you can see that they all sort of sound the same. They all have the same rhythm to them. And so this first one says a certain two-digit integer x, when divided by another integer t, yields a quotient of 7 with a remainder of 2. And then we have this second problem here that has these statements that say when n is divided by 3, the remainder is 1. The second statement says when n is divided by 8, the remainder is 1. And so here in these statements, they dropped the quotient part. That was in the first problem, but they didn't have to. You can just sort of add that to yourself. You can say, so for this first statement, you could have said when n is divided by 3, the quotient is x. And so just make up any variable you want. When n is divided by 3, the quotient is x and the remainder is 1. And that would have basically been saying the same thing that it already says. And so the next problem says, what is the remainder when the positive integer x is divided by 3? And then your first statement says when x is divided by 6, the remainder is 2. Same thing, you could have said when x is divided by 6, the quotient is q and the remainder is 2. The second statement says when x is divided by 15, the remainder is 2. And then this last one says a certain two-digit integer x, when divided by another integer t, yields a quotient of 7 with a remainder of 2. And then this first statement here gets even wackier and says when the digits of x are reversed and the resulting number is divided by 7, the quotient is 7 with a remainder of 1. And so you can sort of see the pattern that I'm talking about. When something is divided by something, the quotient is something and the remainder is something. And so why do I always take note when I sort of hear this pattern? I mentioned before that sometimes with remainder problems, you have to generate examples or generate sequences and sort of look for patterns that way. But other times you can sort of do them algebraically. You can make equations and then use those to solve for what you're looking for. And it is usually problems that fit this sort of mold that I can make algebraic equations out of. I can translate these words into numbers. And so let's talk about how we do that, because with remainders, it's a little bit trickier than just sort of straight algebra. And so say I have this statement here that fits our pattern and says when x is divided by 5, the quotient is y and the remainder is 2. And so oftentimes when I ask people to translate a statement like this, they'll just sort of translate the words literally, and they'll get something like this. They'll say, okay, when x is divided by 5, that is equal to some quotient y plus 2. And they'll say this is their, they'll make this equation. And so the question is this an accurate translation? And one way you can test whether or not this is an accurate translation is you can come up with, think of a value for y, and that will give you a value for x, and then see if it makes sense when you plug it into the statement here. So let's say, I was to say y is equal to 4. So y plus 2 would be equal to 6. So that means x over 5 is equal to 6. And that would mean x is equal to 30. So does this make sense? So if I read this statement again with these numbers, it would be when 30 is divided by 5, the quotient is 4, and the remainder is 2. And so is that right? It's absolutely not right, because when 30 is divided by 5, the quotient is 6, and the remainder is 0. And so this is not an accurate translation. Let's keep this actually. And so this is the problem where you got to use a little bit of critical thinking when translating these remainder statements. And another issue with doing algebra on these remainder problems is it makes it hard sometimes to manipulate these equations when you're dealing with remainders. Because remember, remainders always have this restriction where the remainder has to be less than your divisor. So let's say you had an equation like this and it wasn't an accurate translation. And then you said, okay, I want to get this in terms of x. And so you multiplied both sides by 5. You would get something like x is equal to 5y plus 10. And so this is why it's tricky to manipulate sort of these remainder statements once you've translated them. Because what did we just do here? So we got this equation here, x is equal to 5y plus 10. But now if this is our remainder is greater than our divisor. Our divisor was 5. And so it's hard to take into account algebraically this this restriction that you have. In other words, remainders are sort of real-world situations that follow their own sort of logic, and it's hard to incorporate that logic when you're just manipulating equations using straight algebra. And so here our remainder is no longer less than our divisor. And so how do I translate these statements? And I want to be able to translate them so no manipulation of any sort is needed. And so to talk about what the right translation is, let's talk about how that sequence we had in our previous video. And I'm just not going to write out the whole sequence, just pull some numbers. So let's say we had 17 over 5, 18 over 5, 19 over 5, and then I'll just choose a few numbers further down. So 44 over 5 and 57 over 5. Let's see. And for each of these, you can come up with, if you wanted an answer for what these are equal to in terms of remainders, what did we say these were? So we said here this would be 3 remainder 2. This would be 3 remainder 3. This was 3 remainder 4. This one, what would this be? I believe as close as you can get is 40. So that's 8 remainder 4. And this would be 55 is as close as you can get. So 11 remainder 2. So how did we get each of these answers here? So what we said was, in this case here, so we're trying to get to 17. And so we say 17 is equal to, and we said that's equal to 5 times some multiplier, and that multiplier is an integer, positive integer, where we're trying to get as close to 17 without going over. So in that case, this is 3. And then your remainder is what is ever left over. So 5 times 3 plus 2. And then here we have 18 is equal to 5 times 3 plus 3, because that's how much is left over. And that here, be 19 is equal to 5 times 4. All right, 5 times 3 plus 4. So here we're trying to get to 44. So 44 is equal to 5 times 8 plus 4. And here, 57 is equal to 5 times 11 plus 2. So if we were to translate the equations we have here into a sort of a generic sort of equation, you can see our numerator here is equal to, in this case, 5. So that's our divisor times some multiplier. And this multiplier here is just going to think of it as it's sort of an independent variable. It's just going to be a positive integer, and it's going to be the one that gets you as close as you can to your numerator without going over, plus your remainder. So if we did the same thing here, with this statement, how would we translate it to match the equations we have here? So here we would be saying x is equal to 5. And so this multiplier here is your quotient. And so when they say the quotient is y, they're saying x is equal to 5 times y plus 2. And once you have this equation here, you should be able to generate a bunch of examples very quickly of what x could be. And the easiest thing to do is to just, your sequence is going to go up by the same amount every single time. So if you just generate the first two numbers x can be, you can get the whole sequence. And so what that means is you're testing numbers values for y. So starting at 1. So if y is equal to 1, so we're coming up with values for x. So 5 times 1 plus 2 is just going to be 7. 5 times 2 plus 2 is just going to be 12. So we're going up by 5 every time. And so if I wanted to come up with a bunch more examples, I could. And so if we wanted to, so in this case, this was when y was 1, y was 2, 3, 4, 5. So we can test one of our examples here. So when 17 is divided by 5, the quotient is 3 and the remainder is 2. And that is accurate because we had here 3 remainder 2. So this is a very useful translation to be able to make, because you can then use this if they gave you two equations, for example. You can maybe use algebra then to solve for x or y. Or, and this is probably more common, if you have this translation, you can just use it to generate a bunch of examples really quickly of what x could be and what the pattern is in this remainder sequence. And so let's do a problem now where we can do some algebra using our remainder translation skills. When x is divided by 3, the quotient is y and the remainder is 1. When x is divided by 8, the quotient is z and the remainder is 7. Given that y is equal to 10/3 z, what is the value of z? Okay, and so these fit the pattern of our remainder translations. And so if I were to translate each of these statements into an equation, so when x is divided by 3, that means x is equal to 3 times our quotient plus 1. And then we have a second equation here. When x is divided by 8, the quotient is z and the remainder is 7. And so this one is telling us that x is equal to 8 times our quotient z plus 7. So now we have two equations, so both in terms of x, and therefore we should be able to set those equations equal to each other. So we can get, in other words, if they're asking for z, right, then we have 3 variables to start out with, x, y, and z, and we only have 2 equations. And so we got to start cutting down our variables, because if we have 2 equations, you should only have 2 variables, at least if you want to solve for those variables. So we can get rid of our x by setting 3y plus 1 equal to 8z plus 7. And so we know we want to get rid of our x because the information they give us here is y in terms of z, and therefore having an equation with an x in it isn't going to be solvable. And we're trying to solve for z here. And so if we're trying to solve for z, we want to put y in terms of z, which is exactly what we can do here. And so now instead of saying 3y plus 1, I can say this is 3 times 10/3, 10/3 times z plus 1. That is equal to 8z plus 7. And now all I got to do is solve for z. And so 3 times 10/3 z, so this should just be 10z plus 1 is equal to 8z plus 7. subtract 8z from each side. 2z plus 1 is equal to 7. 2z is equal to 6. Therefore, z is equal to 3. So what is that? E looks to be our answer. And so can we use this as a check here? So if z is equal to 3, y should be equal to 10, right? And so does that fit with our equations here? And so if this were true, x would be equal to 8 times 3. X would be equal to 31. So let's see if that works. So when 31 is divided by 3, so what should this be? This should be 10 remainder 1, right? So when x is divided by 3, the quotient is 10 and the remainder is 1. So this works. And how about over here? So here we get when x is divided by 8, so that's 31 over 8. And so this should be 3 remainder 7. So when x is divided by 8, the quotient is z, which is 3, and the remainder is 7. So these check out. And so there's a case where you can use algebra to solve for your remainder problems as long as you can translate your remainder statements accurately. And so that is a very useful skill to have, and all it really requires is just being able to pick up sort of on this pattern here. We will do some more problems now with some more complicated translations and problems that maybe require a mixture of algebra and looking for patterns. So we will do those in the next few videos.